Let's examine the physics surrounding a charged particle moving in a uniform magnetic field as shown in the picture. The uniform magnetic field is represented by little x's going into the page, and we've got a value of the uniform magnetic field as 50 Gauss. We're not going to change that value. We're going to fire a proton, a positive charge, into this magnetic field at a speed of 300,000 meters per second. When I fire the proton, it's going to have a velocity vector straight upwards, and the magnetic field is into the page. And if we use our right-hand rule, where our fingers go into the page to represent the magnetic field and my thumb points upwards in the direction of the velocity, you should find that there's a force directed to the left. Let's examine what happens when I fire this charge into this field. We see that it moves in a semicircular path off to the left. Now, why does it move in a circle? As soon as the particle enters the magnetic field, the force is acting on it. Because the force is at right angles to the velocity, it serves to change the velocity's direction only. It does not speed it up or slow it down, simply because this force is not aligned in the direction of the velocity vector itself. If it was, the charge would speed up or slow down, as we've seen in kinematics and dynamics. The fact that it's 90 degrees to it creates circular motion. The second this charge enters the field, it changes direction. The force acts on it and deflects it to the left. Now, if you reposition your thumb in this new direction, you'll see that the force is now down to the left a little bit. The palm of your hand will be facing down to the left. And if you follow this completely around the path of this charge, it'll move in a circle. Now, the reason that it interacts in the first place is because moving charges create their own magnetic fields. And we know that two magnetic fields will interact with each other. They'll either attract or repel. And we see that interaction with the right-hand rule. Let's examine the effects of increasing the external magnetic field to a value that's double. If we start at 50 and we double it to 100, we should get a stronger interaction. Let's see what happens. You see that it bends the charge more vigorously and the circle is actually smaller. The diameter of that circle is about 3.9 meters. Let's go back and revisit our original one. The diameter of our original circle is about 7.6 meters. Double. So when I double the magnetic field, the diameter of the path is halved. It's an inverse relationship. Now let's see what happens when we change our value of our velocity. The original velocity was 300,000. Let's reduce it to 100,000. Much slower. When I run it now, the circle is quite small. The fact that it's going so slow gives it lots of time to interact with that external magnetic field, and the external magnetic field bends it quite rapidly. In fact, it bends it to a value of 2.5. So when the velocity is decreased, the diameter of that circle is also decreased. Lastly, let's examine the effects of the value of the charge, whether or not it's positive or negative. If I change the charge to a negative charge, we would expect it just to reverse direction, and we see that it does.